Some months ago the student organizations had ended Mr. Landau's teaching activities. Here we are less interested in the obvious reasons than the deeper background of the event. One needs a sample to represent what is seen, that the representation of peoples with different races as teachers and students cannot fit together. It is known that race spiritually structures the personality and is present in all outer expressions of life. The instincts of the Göttinger were felt in Landau with a type of un-German style in the way that things are done. We should make one example so that we can be clear. In his newest publication of Differential and Integral Calculus, Landau has a want for a more precise and more seamless way of knowing methodology, as he wants to spread the most appropriate way of instruction, which can be seen in Chapter 1. We can see in example 16, the trigonometric function, sine and cosine, which is defined in the following power series. Sin equals sigma equals 0 infinity 1 2 plus 1 2 plus 1. Equation 262. It gives that this is correct, pi 0 with cos, pi/2, equals 0, cos, x, 0 for 0 equals x equals 2. In other words, cos, y, equals 0 has the smallest positive even solution. Definition 61, the global constant of page 262, which would become a permanent designated constant with pi. How large is, what has to do with the similarly named number familiar from school, what the Landau sine and cosine have to do with the well-known functions of the same name. The reader is told nothing about any of this. True, we hear in the preface that in the actual lectures, geometric applications take up a significant portion. But the book does without them, because the potentially necessary presentation of the axioms and elements of geometry, which, Landau assures us, one is expected to know, would require a separate volume. The difficult task was merely to select from the many existing facts those which he would most like to present to students at the beginning of their studies, to arrange them in a purposeful order, and above all to uncover the often unspoken definitions and theorems that serve as the glue for constructing the entire edifice. We have seen how these maxims affected the treatment of the trigonometric functions. These functions are arbitrarily torn out of their clear mathematical context, as if they did not derive their meaning and significance solely from that context. It may be interesting to see how the various properties of these functions follow from the power series. But it is nonsense to fob off beginners with that. The German beginner is not so miseducated that he wants to forget the meaning and significance of things because of such jokes. It is also not enough for him to be told afterwards that one can apply this or that one can later show that the oddly defined number pi is the well-known one. He marvels, and with marveling, for us, knowledge begins, whereas in the style of Landau, marveling stands at the end. We want the presentation to be organic, that is, such that the theory arises from the natural foundational conditions. How can that be done? The approach of a German mathematician, namely Erhard Schmidt, is characteristic in this regard. He too does not overlook the difficulties that trigonometric functions pose for a seamless, systematic development of differential and integral calculus. But as a German, he does not even consider replacing what is required with an arbitrarily conceived construction. He places the treatment of area at the beginning, that is, he treats the theory of the definite integral before differential calculus. This approach allows him to establish a solid conceptual foundation for the number pi and enables the trigonometric functions to be integrated into the system from their natural mathematical setting. The system is oriented toward the nature of the things themselves, its structure is organic. In contrast, the Landau style is detached from reality, hostile to life, and inorganic. The approach of Erhard Schmidt, however, is concrete, intuitive, and yet fully consistent with all logical requirements. In the Foundations of the New Society by Paul Ernst, we find the sentence on p. 200, Jewish thinking always starts from something already thought, it never arises from nature and human experience. One may take this sentence as a definition of what is meant by the term Jewish thinking type. Modern man's intellectual arrogance has not only forced science into a one-sided track and endangered culture and life, but, hand in hand with all this, also ruined education, says Jansch on p. 121 of his Foundations of Human Knowledge. Now, I hope to have clarified what the Göttingen students were concerned with in their opposition to Mr. Landau, a people that has come to understand how foreign ambitions for power gnaw at its very marrow, how alien elements are working to impose a foreign nature upon it, must reject teachers of a type foreign to it. It must place value on having its youth educated in the national, folkish, spirit, on ensuring that its youth learns to recognize, to feel, and to uphold the national character even in the sciences. Everything we do and think arises from our human nature, is connected to it, and derives its style from our race and our blood. So too with science and its teaching. What suits us Germans is what corresponds to our nature. That also determines a selection of problems, but even more so a distinct German style of treatment. Our innermost being stirs when we feel this nature being violated. In that moment, we become even more conscious of our own kind. As part of my lecture, this was a first example of how a personality structure rooted in race is expressed in the style of mathematical work, and also of how important these matters are for the design of education. This is not about the strength or level of scientific achievement, but rather about its manner and style. Thus, the preceding remarks do not concern the undisputed merits of Mr. Landau in the discovery of new scientific facts. Another example, on p. 213 of Science and Hypothesis, Poincaré describes the impression that Maxwell's electricity and magnetism makes on a French mind. When a French reader opens Maxwell's book for the first time, a feeling of unease, often even of mistrust, mixes with his admiration. The ideas of the English scholar are likely so difficult to introduce in France because the education received by most Frenchmen especially predisposes them to value precision and logic above all other qualities. The French masters from Laplace to Cauchy started from clearly stated hypotheses, derived all consequences with mathematical rigor, and then compared them with experience. With Maxwell, however, the path is different. The starting point is not hypothesis, but rather real-world experience. This leads to certain conceptually graspable ideas. Ultimately, it becomes clear how the formal apparatus of mechanics can serve to describe the connections between the electromagnetic concepts derived from experience. Here, too, we see two types of mental structure facing each other. In the terminology of Jantia psychology, it is the S-type of the French and the I-type of Maxwell. The S-type values only that in reality which his mind projects into it, as Poincaré also notes, he constructs, behind the matter perceived by the senses, another kind, which for him is the only true one and which possesses only geometrical properties. In contrast stands the I-type, wide open to reality, allowing the influences of experience to flow into him, and striving with all senses, that is, for the mathematician, with intuition and thought to grasp as much of reality as possible. We recognize again the types we previously contrasted when considering Landau's style. Even where Poincaré does not explicitly intend it, he describes typical mental structures. On page 27 of Science and Hypothesis, we read, "The intellect has the ability to create symbols, and in doing so, it constructs the mathematical continuum, which is nothing but a specific system of symbols." This observation is characteristic of the S-type in Jantia psychology. And on page 51, the axioms of geometry are conventions. Let's clarify what Poincaré means with a concrete example. In Goursat's Cours d'Analyse, chapter 13, complex numbers are defined as, an imaginary or complex quantity is any expression of the form a plus ib, where a and b are real numbers, and I is a special symbol introduced to give algebra greater generality. Essentially, a complex number is simply an ordered pair of real numbers. Although expressions of the form a plus ib have no inherent concrete meaning, it is agreed to apply to them the usual rules of algebraic calculation, by also agreeing to replace I superscript 2 with 1. This briefly describes the theory of complex numbers developed by Cauchy. Notable are the phrases simple and it is agreed. Now compare this with what Gauss says at the end of his discussion of the Gaussian number plane, Vereen, 177, 1825 here, the demonstrability of an intuitive meaning of square root 1 is fully justified, and nothing more is required in order to admit this quantity into the domain of arithmetic objects. And again, in Cauchy's Cours d'Analyse, 1821, the chapter on imaginary numbers begins, in analysis, a symbolic expression or symbol is any combination of algebraic signs which in itself means nothing, or to which a value is assigned that differs from its natural one. Contrast this symbolic approach with the organic and concrete way in which Gauss and Hamilton introduce complex numbers as actual objects, vectors or number pairs, how operations with them are substantively defined, and how, suddenly, each statement becomes content-based rather than merely symbolic. To us Germans, the Cauchy-Goursat approach evokes intolerable discomfort. If someone objects that the Cauchy-Goursat method is outdated, they should note that it is just as old as that of Gauss and Hamilton and recall Poincaré's own principle. That makes it clear how much the differences and discomforts stem from mental structures. Certainly, environment and education influence an individual's approach, but in the case of the originators of these theories, the racial structural root seems entirely evident to me. The inability to understand also comes through in the words Jacobi uses in his lectures on number theory, pages 196 to 197, about Gauss's theory. Gauss gave a geometric intuition through the fields of an infinite chessboard. But he places too much weight on this playful symbolism, so that one might think he intended to construct the imaginary quantities, which had already been done by Wallis and later under Lagrange's influence by Fonsenek. In general, Gauss and Jacobi offer a good further example of opposing intellectual structures, the Nordicphalian Gauss versus the Oriental Jacobi. Already the ruthless will to assert one's personality sets Jacobi apart from the quiet, persistent Gauss, who values only well-formed achievement and nothing of self-promotion, as he once said himself. The contrast in types comes through clearly in a passage from Jacobi's number theory, p74, since Gauss usually presents his results and proofs without any visible interconnection, completely rigid and frozen, like riddles that must first be thought, or elsewhere to Bessel, Gauss, who in modern times seems to have invented this tedious rigor. Jacobi could speak differently, too. When the Göttingen Society made him a foreign member, he wrote in his thank you letter about Gauss's ideal rigor. But let's hear Gauss himself describe his own method, the wish I have always had in my work, to give them such completion that nothing more could be desired, makes them extraordinarily difficult for me. Or his motto, few, but ripe. This characterizes Gauss's serious nature. It is quite instructive to compare how Gauss and Euler and East Baltic, Dinaric mixture approach the same problem. The task is to find a number that leaves given remainders when divided by several divisors. With Euler, it is a comfortable handling of a calculation method. With Gauss, the question of solvability is first thoroughly clarified, and the Eulerian method of calculation is then justified as an appendix. In this way, Gauss achieves a complete clarification of the problem, whereas Euler's method runs into a dead end. Two more statements from Gauss himself. I have the bad habit of only taking a lively interest in mathematical matters where I may anticipate clever combinations of ideas and results that recommend themselves through elegance or generality. In integral calculus, I have always found far less interest in those parts where it is merely a matter of substitution, transformation, etc. In short, a certain cleverly handled mechanism in order to reduce integrals to algebraic, logarithmic, or trigonometric functions, than in the more exact and deeper study of those transcendental functions that cannot be reduced to the former. In Gauss, we find a matter-of-fact, active, evaluative engagement with things, persistently overcoming difficulties with all his strength. In Euler, we find a playful unity with things. In Jacobi, it is the assertion of the human being and his will over what is given; in Euler, a childlike unity with the world. In Gauss, distance from things and independent judgment, openness to them as with Euler, but without unity with them. The difference between Gauss's and Jacobi's approaches can also be demonstrated through a problem both worked on, Gauss's mechanical quadrature. What Gauss derives artfully through conceptual means, theoretical discussion, and complete induction, Jacobi dispatches with direct calculation. It may also be telling that under the influence of Jacobi and his school, German mathematics began to lose its living connection with applications. Pure mathematics emancipated itself as an ornament of the human spirit, standing freely on its own, dealing only with what is thought and what follows from it, without regard for real-world meaning. Under the direct influence of Gauss, the connection to practical applications remained alive. All of Gauss's students were somehow connected to astronomy. His later successors, Riemann, Klein, are typical examples of a mathematical approach developed in contact with the world outside ourselves. Being of low German descent, like Gauss, they share something in common in the peculiarly visual and tangible nature of their thinking. These are racial characteristics, which Klein described in portraying his father as a tenacious will, an unrelenting diligence, a sober sense of reality, absolute reliability, and carefully considered frugality. These are qualities that can also be found in the 4th and 5th grade Low German mathematicians, Dedekind and Weierstrass. I would now like to focus particularly on Klein and Weierstrass. Despite mutual respect, at first glance both men were opposites, and their mathematical styles seem completely different, just as the outward appearance of both men had little in common. Yet, in both men, it is a matter of balancing the seemingly opposing tendencies of intuition and reasoning, of intuitive and conceptual clarity. In mathematics, intuition and thinking are names for the sensory or intuitive and the rational sources of research and teaching. An intuition that does not withstand logical reflection is also rejected by Klein. However, his stylistic type forbids him from turning his back on intuition when logical criticism encounters inconsistencies. For him, the consequence is the education of intuition it must learn from critique. This leads him to a peculiar way of looking at things from all sides and examining them until he gains the certainty that nothing essential has been overlooked. His style of presentation and lecturing is not strictly deductive, but explanatory. Gauss and Riemann may have found their results in a similar manner, except that in Gauss, a strongly abstract logical sense of form layered over everything, which then sought to anchor the discoveries purely through logic. This is missing in Klein, and yet, to my knowledge, Klein never put forth a result that did not withstand all criticism. Weierstrass was likely more influenced by Gauss's sense of form. Thus, Weierstrass's style, compared to Klein's, has something heavy, austere about it. In terms of racial anthropology, one might involuntarily think of the Falisk, Phalian, type, which in Gauss was mixed with the Nordic, whereas in Klein, something Dinaric may have been added to the Nordic base. In Weierstrass, there is no rejection of the intuitive, only a tenacious and stubborn adherence to the set goal, to construct a logically perfect system. So, in his polished presentations, one notices nothing of the high regard for applications that speaks from his inaugural lecture, and which he, a very broadly educated man, demonstrated elsewhere as well. It is a deliberate restriction, a thinker under strict self-discipline. For he despaired of incorporating intuition into his system. The unity that at least still existed within Weierstrass himself disappeared only among his students. This was because his influence took place during a time when, in other places, there seemed to be a compulsion toward abstraction and formalization. Strangely enough, the paradoxes of set theory did not lead to a turning away from a reality-detached use of formal reasoning. Rather, in line with the disposition of those primarily involved in set theory, the development took the direction of banning intuition altogether. The errors and paradoxes were supposed to come from human intuition and human understanding. They were to be driven out through the absolutization and dehumanization of mathematical science. What Jansch called the Cartesian fear of error has had a lasting and detrimental influence on our academic and educational system. Education forgot everything else in the constant concern to demonstrate to students and even to school children the methods that Weierstrass and others devised to guard against the misguidance of undisciplined intuition. Weierstrass himself never published anything about these methods; he applied them, like his immediate students, to concrete problems. Only his epigones, followers, came to regard these safeguards as more important than meaningful engagement, and in their focus on method, they forgot to look at purpose and meaning, content and organic connection, thus aligning themselves with the harmful influence of the Jacobian school. How such scholastic rigidity operates was recently demonstrated to me during a break in duty by an SA comrade, who posed the same question to several mathematicians and some untrained men. The untrained men answered it instinctively and correctly, while the mathematicians began to overthink it. Klein, in his down-to-earth manner, recognized these dangers. He consistently fought for the fruitful collaboration of intellect and the senses in both research and teaching, no stunting of one at the expense of the other. The opposite type, represented here by Mr. Hahn in Vienna in his lecture on the crisis of intuition, claims that the turn away from intuition lies necessarily in the trajectory of mathematical development, that it is an inevitable goal of progress, in which every mathematical field becomes nothing more than a logical construction. Certainly, the less intuitive something is, the fewer opportunities exist for the expression of our racial character in mathematical activity. The absolutization and dehumanization of mathematics works in favor of this opposing type. To us, however, this surrender of mathematics to the opposing type appears neither necessary nor welcome. Furthermore, the very possibility of such absolutization has become highly questionable due to Gödel's investigations. In attempting to prove the impossibility of contradictions a priori, axiomatics has entangled itself in difficulties. There can be no autonomous mathematical realm independent of human activity and intuition and thus not independent of the styles through which human racial belonging expresses itself. Originally, axiomatics did not emerge with such totalitarian claims. The axiomatic method was initially a procedure in which meaning and openness to given realities were well balanced with logical concerns. Axiomatics, so to speak, constructs a logical image of what is truly given by building a logical structure from individual features of reality. In this way, it fully corresponds to the I-type of organic thinking that remains close to reality. Indeed, the originators of axiomatics, Dedekind and Hilbert, can themselves be classified as belonging to the I-type, specifically the idealist form of this type. A certain precedence of thought over intuition is noticeable here, just as psychological typology observes in certain forms of the I-type. From there, a bridge is certainly possible to the S-type, which rejects any relation to an external reality not conceived by thought. If one examines the proponents of this absolute axiomatics, one finds confirmation of what typology asserts about their belonging to the S-type, even extending to the pathological tendencies that supposedly predispose one to the S-type. In fact, I am of the opinion that the entire foundational dispute in mathematics can be explained as a conflict between opposing psychological types primarily, therefore, as a racial conflict. The rise of intuitionism seems to me only a confirmation of this view. Untouched by all foundational disputes remains the compromise found by Klein, which endures as appropriate to our German nature. The focus on what is naturally given, on organic interconnections, gives us the right sense for what is important and unimportant, essential and inessential. Our rootedness in our people gives our activity and our thinking their style. Certain stylistic variations are still entirely possible here, as a look at the various great German mathematicians we have discussed shows. It is telling that countertypical mathematics does not like to speak of meaning and significance. While a German mathematician strives to uncover the true reason for a result, that is, to find the organic position of the result, the countertypical approach favors derivations in which one can admire the skill and cunning in handling technical apparatus. Admiration for the juggler distracts attention from the object with which he juggles and sometimes allows the emptiness behind the dazzling facade to disappear from view. The German mind is not satisfied until form and content are brought into proper balance, until meaning and significance are clear. One need only examine the two surviving versions of Gauss's foundational work on surface theory. On one hand, one will recognize the intuitive grounding of Gauss's thought, while in the final version, one can see how Gauss labored to find a form that would everywhere reveal what he believed to be the true foundation of his results. To conclude, one more example: many have tried to see in Klein a precursor of formalism. Klein resisted this with all his might. In fact, Klein, inspired by geometric principles of transference, was the first to bring the concept of isomorphism, i.e., the identical logical structure of different mathematical domains, into general awareness. For the formalists, this was a signal to declare, thus, content does not matter. For Klein, however, the content was the main thing. The identical logical structure was merely a means to make results from one domain applicable to another. For Klein, the emphasis was not on the identical logical structure of different domains but on the fact that the same logical state of affairs could be endowed with different intuitive content. In this way, various parts of the same logical theory can be developed using ever-changing, suitably chosen intuitive material. Klein's idea allows us, as I once formulated it earlier, to be carried along by the suggestive power that lies in the fact that, between two domains with the same logical structure, the objects and operations in one may be more familiar to us because we associate a clearer mental image with them than with the corresponding objects of the other, even though, from a purely logical standpoint, they involve the same train of thought. Here, we see how all the means of sense and thought are harnessed to gain insight into real connections. Everyone has had such experiences with the principle of duality. Everyone knows how theorems and arguments suddenly gain life and flexibility when dualized. Similar experiences arise with more complex structural equivalences in abundance. Klein sees in this the beauty and vitality of mathematical theorems. He sees in them more than the pale skeletons in the formalism's desert sands about which no one knows what they mean or what purpose they serve or once served. Observations: I have sought to demonstrate that there are distinct styles in mathematical work, that blood and race influence the nature of mathematical activity. Klein was well aware that racial differences underlie questions of style. In 1893, at the World's Fair in Chicago, he spoke words that, translated into modern terminology, would read: I am inclined to believe that highly developed spatial intuition is a distinctive characteristic of the Nordic race, while critical sense and purely logical elements are more pronounced among Romance peoples and those of Jewish disposition. In my discussion, through examples and broader, one particular circumstance deserves special mention. If one superimposes onto an ethnological map of Germany showing the distribution areas of light and dark races, the regions where our great German mathematicians have been rooted for generations, a remarkable discovery emerges: nearly all of them originated from the territories of the light races, often bordering the dark race areas, with Euler appearing as the sole case falling entirely within the dark race zone. If you seek practical implications from these observations, I would offer the following: when our population policy emphasizes Aufnordung, Nordicization, it seems to me that favoring the Nordic component in our racial composition could be advanced by aligning education with the intellectual style characteristic of our great German mathematicians. With the exception of Euler, They all exhibited strong Nordic influences. From my perspective, this lends deeper significance to Klein's proposed school reforms, adapting our educational system to the racial type to whom we wish to grant increasing influence in guiding our nation. Hence, education should be structured as Klein advocated, balancing intuition and logical thought in a manner harmonious with the type most receptive to reality through all senses. Another practical implication, when justifying the necessity of mathematics for the nation, people often emphasize its practical applications, a point that also features prominently in Klein's reform plans. Just last evening, Admiral Conrad eloquently explained to us the immense value of mathematical work for our nation's military readiness. However, it seems to me that mathematics does not need to justify its connection to the vote solely through practical utility. My arguments have shown that this supposedly international science cannot, in how it is practiced, be separated from the influences of blood and race. Thus, mathematics also appears to me as a field of folkish, ethnic national, expression, and everything in which our national character vigorously manifests itself requires no further justification. Our task is simply to recognize clearly what constitutes our German distinctiveness so that we may cultivate it productively. My lecture aimed to contribute to this understanding. Once we grasp our own nature and where it can be most effectively applied, we have the best chance of standing firm among the nations, even if we voluntarily reject foreign influences that, due to the conflation of state and ethnic identity, have burdened our German essence until now. Reflecting on our German character will strengthen, not diminish, our power.